Good morning, or whatever time of day you're watching this. Let's talk about 10.6 and 10.7, which is on activation energy and the reaction process. So we talked about Gibbs free energy. We talked about reactions and whether they would be spontaneous or not. Spontaneous meaning a physical or chemical change that occurs with no outside intervention. For example, if we look at the reaction of iron rusting, where we have iron as an element, solid, and oxygen gas, which is in our atmosphere, those will spontaneously react to form iron oxide, Fe2O3, which is what we call rust. Notice that the enthalpy for this reaction is negative. That is very conducive. Whilst it doesn't guarantee a reaction to spontaneous, it's very conducive to a reaction being spontaneous. It's exothermic, it releases energy, and we know that the universe tends towards disorder or releasing energy. All right, so just because something is spontaneous doesn't mean that nothing is needed. We still need sometimes a little bit of energy to get the reaction started, and that's called the activation energy. If we think about the combustion reaction that happens in your engine, so if we look at your engine, we have, well, not exactly your engine, but we'll look at a four-stroke engine. We have the intake step, which pulls in your gasoline and air. Then you have the compression step, which is going to put it under pressure, putting the molecules more close together. And then here is our activation energy. Our spark plug is going to give a little bit of energy in the form of a heat spark. And that's going to actually start the combustion reaction. It's a little bit we needed to then set off the full combustion reaction. And then you have the exhaust step, which lets out the product of that combustion reaction. And we can look at that. We can look at the combustion of methane in the presence of oxygen to form carbon dioxide and water. And again, this is an exothermic reaction. So this activation energy, if we officially define it, it's the minimum energy needed to initiate or to start a reaction, and we call it E sub A. This is always a positive number. You always have to add in this energy. We never release energy for activation energy. We always add it into the reaction. And it forms what we call the activated complex, or our intermediate step, our transition molecule. It's not our reactants, it's not our products. Bonds have been broken, new bonds are forming. It's our intermediate. So we can think of it as something like this. So A is our reactants, and B is our product. So we start with the reactant. This rock is kind of sitting there at the base of a hill. To get the rock from where it is to the ground, we have to put in some amount of work. That's our activation energy, the amount of energy needed to get that rock rolling and to put it up that hill a bit before it'll roll down and form the product. At the very top of this hill is what we call the activated complex, or a kind of intermediate point in the reaction. And so what we can do is, for all of our reactions, is we can diagram them or create a graph of what's going on. So if we look at this graph, what we have is the progress of our reaction from the start to the end of the reaction. And on the y-axis, we have potential energy measured in kilojoules. And so we have increasing energy on the y. So in this diagram, our reactants are starting off on the left-hand side. It's the start of the reaction. They have some amount of energy in kilojoules. To go from the reactants to the transition state, or the activated complex, it requires our EA, our activation energy. So we need to add in that positive amount of energy to get from the reactant to the transition state. Once we get there, then we have enough energy for the reaction to continue, and we form our products that you can see on the right-hand side. The difference in energy from the reactants to the products is our enthalpy, which we've seen before. So this diagram tells us the energy of the reactants, the energy of the products, the activation energy, how much we have to add, and the overall change in energy from start to finish, or the difference between the products and the reactants' energy. And so what we can look at is how these graphs look different when a reaction is endothermic versus exothermic. So if we take a look at this graph, what you notice, or what I hope you notice, is that the products have more energy or a higher energy than the reactants. So our products have higher potential energy than our reactants. So our reactants, what we say is our reactants start low, and then it takes a lot of energy added in to start the reaction. Our EA, our activation energy, is very high. And then our enthalpy is positive. More energy went in than energy released. Our products are sitting at a higher energy level than our reactants. So how does it look different when it's exothermic? Well, in an exothermic reaction, the products have less potential energy than the reactants. Or in other words, the reactants start high and the products end low. We need less activation energy, and our enthalpy is negative, or the change, we lost energy. We gave off energy in an exothermic process. So the last thing I want to talk about is a catalyst. For an activation diagram, or well, really in a reaction, we can add a catalyst. Now you might remember this from biology. Your biology teacher might have called it an enzyme. An enzyme is a catalyst, just specific to a living organism. So what's a catalyst? It's a substance that increases the rate of our reaction. It makes our reaction happen more quickly without being used in the reaction. So it's not actually part of our overall reaction. We're not going to write it into the formula of our reaction, but it is going to make it happen faster. How does it do it? It lowers the activation energy. So if we go to our diagram, on our diagram in orange, you can see the normal activation energy. When you add an enzyme, or in general, a catalyst, what it does is the height of the activation energy, the amount of energy you need to add in, is lower. I like to think of it like a coupon. There's the normal price to buy something. If you have a coupon, it lowers the price to buy it. More people will likely buy that product if you have a coupon, because it lowers the cost to get it. Just like a catalyst lowers the activation energy needed for the reaction to begin, so it's more likely to occur because that lesser amount of energy is easier to find. All right, I would recommend that you pause here for a moment. That's the end of the portion that I call 2.6, and just take a quick break to reflect on what you've learned before we continue on to 2.7. Excuse me, 10.7. All right, so 10.7 is about the reaction process. So we talked about activation, energy, and catalyst. Now we're going to look at what makes a reaction happen. Well, a reaction occurring is determined by what we call collision theory. Collision theory has two postulates. That is, if a reaction is going to happen, then the reactant particles must collide. So they have to bump into each other, and they must collide with two specific things. They must collide with sufficient energy and in the correct orientation. So if we look at, again, a diagram, we have a reaction between a chlorine and NO2Cl. Now, for us to get to the transition state and ultimately to our products, they have to collide with enough energy that that chlorine can pull the other chlorine off of the NO2, and it has to hit with correct orientation. If that chlorine bumps into an oxygen, no reaction. If that chlorine bumps into the nitrogen, no reaction. The chlorine needs to bump into the other chlorine, so that's correct orientation, it has to bump into the right part of the molecule, and it has to hit it with enough energy that it attaches to that chlorine and pulls it away. So in this reaction, for it to occur, one chlorine must collide with the other chlorine with enough energy and the correct orientation to knock it off of that molecule. So to start a reaction, sufficient energy and correct orientation. Now, let's say we have that. What's going to determine how quickly a reaction happens are these 5 factors. The nature of the reactants, what they are, their surface area, the concentration of the reactants, the temperature, and whether there's a catalyst present. So let's talk about why for each of those. So the nature of the reactant, how reactive they are. For example, sodium is highly reactive with water. That's part of the nature of what that reactant is. That's going to be a very rapid reaction. Whereas we could look at something like hydrogen, which is less reactive than sodium. So that's just by the nature of what those elements are. Surface area, let's say we have something with a very small surface area. So all those molecules in the middle are shielded by the molecules on the periphery. So we can only react with the external or the ones on the outside and not the internal molecules. But if we break up, say, that crystal into very smooth, small pieces, now we can get at more of those reactants. So the greater the surface area, the faster the reaction, because we're able to access more of the reactants more quickly. If they're locked up, say, in like a sugar cube versus powdered sugar. If you put a sugar cube into your coffee, it's going to take longer to dissolve than if you crush it up into a powder, which increases its surface area. Now, the same idea as surface area is concentration. The higher the concentration, the more reactants there are, the more likely you're going to have collisions, the more rapidly the reaction will occur. Temperature imparts energy to our molecules, so that increases the energy, that increases the likelihood that collisions will happen with sufficient energy. And then we talked about a catalyst. A catalyst provides a place for our reactants to meet up. So we can see we have the surface. It provides a place for our reactants to come to, and it creates the favorable orientation so that that requirement is met more rapidly. Lastly, we can look at talking about the reaction mechanism. What are the steps, or in other words, this is like Hess's law. What are the steps that need to occur for that reaction to happen? Can be a single step or can be multiple steps. In this example, our overall reaction is hydrogen and iodine forming 2 hydroiodic acids. But it actually happens in 3 steps. Step 1, the iodine needs to go from a diatomic iodine to individual iodine atoms. Our hydrogen and one of the iodines needs to react to form a hydrogen and iodine complex and a lone hydrogen ion. And then a single iodine and another hydrogen also need to react to form another hydroiodic acid. So we can see 3 steps needed for this reaction to occur. Even though we would document it as just one single reaction, it has multiple steps in the process. Which then leads us to what we call the rate determining step. This is the slowest step, and that determines the overall rate. You're only as fast as the slowest step. So if we have 3 steps again, the first